At the beginning of April 2014, Heartbleed threatened network security across the world. The media was awash with hyperbole, and online discourse was filled with chaos. During the disorder, I believe important details were both missed and misrepresented. I wanted to tell the story from a software engineer's perspective and outline some of my thoughts on an important historical event. It began with a simple extension to the protocol, a feature to allow secure connections maintain their own availability. This draft request for comment, first presented in December 2011, is the beginning of the Heartbleed story, which continues to deliver bad news more than a decade later. There are many implementations that would incorporate this extension, of which OpenSSL is just one. Started as an open source project in 1998, OpenSSL maintains and develops a toolkit for cryptography and secure communications. Even though it is just one implementation among many, OpenSSL to this day still accounts for a majority of secure public-facing servers on the internet. At the time of the events, OpenSSL was more than 420,000 lines of C code, with only a handful of core developers, most of which had other ongoing job commitments. By late 2023, the project had grown to more than 600,000 lines of C code. An early implementation of the draft RFC in OpenSSL, submitted by one of the authors of the draft, Robin Segelman, arrived for review by the core developer team in the form of a pull request. Robin, at the time, was a graduate student from the University of Münster in Germany, working on a research project to improve OpenSSL by eliminating bugs and creating new features. He had been doing so for more than 2 years, and in this time he had successfully fixed over 40 bugs, mostly in relation to secure communications. He had also implemented 2 new extensions to the protocol, SCTP support for DTLS and DTLS renegotiation. SCTP allows for a single connection to handle multiple data streams, and DTLS renegotiation allows connection recovery upon loss of data between endpoints without requiring a full reconnection sequence. The Heartbleed extension implementation was similar to his other feature contributions in that they have their origin in RFCs, of which he was one of the authors, and also that it would be enabled by default. All but one of Robin's prior work in the OpenSSL repository were reviewed, approved, and merged by one individual, Dr. Stephen Henson, also known as Steve in the commit logs. Late on the 31st of December 2011, the pull request was merged by Steve. The review process at the time was intended for functionality as well as other purposes, making potential security vulnerabilities more difficult to spot as it was not the sole focus at any point. Steve, a British software engineer with a PhD in graph theory mathematics, was one of the project's original creators and now a core developer. At the time, he was the only full-time employee working on the project, and he merged about 60% of all pull requests. With the offending source code on the master branch, it was now only a matter of time before it would begin exposing itself to the wider world. About 6 weeks after the merge, the official RFC was released. This would be the official document that implementers of TLS and DTLS protocols would need to follow in order to be compatible with each other. It contains relatively minor changes from the draft, most of which are just the use of more precise language. One notable line reads, "If the payload length of a received heartbeat message is too large, the received heartbeat message must be discarded silently, which if followed diligently, Heartbleed may not have occurred." Another ominous addition towards the end of the document reads, "The security considerations of RFC 5246 and RFC 6347 apply to this document, which refer to the TLS and DTLS protocols, both of which were affected by Heartbleed." To understand Heartbleed, we must first have some understanding of the secure connection protocols TLS and DTLS, and then how the Heartbleed extension is intended to operate and what its purpose is. TLS and DTLS operate similarly, except that one is over TCP and the other is over UDP. Once the secure connection is established, encrypted data can travel between the endpoints. The issue the Heartbleed extension attempts to solve is if the endpoints do not communicate with each other for a period, there is a risk the connection will be terminated and have to reconnect. This may be much more computationally expensive because the connection will have to go through the startup connection process and perhaps additional authentication processes, which may diminish the quality of service or increase latency. A termination may happen due to a timeout or an overzealous firewall, but one possible way to mitigate them is to periodically send and receive small amounts of data. The keep alive could be achieved in the data layer, but it would be difficult to standardize because it would be within the bounds of other protocols built on top of TLS, like HTTP. This is why the Heartbeat extension approach is to place the keep alive within the TLS layer, so that the data can be ignored by the underlying protocol. Unfortunately, this makes it particularly dangerous if there are vulnerabilities in this area of the code, because the application sending and receiving data may be unaware of the presence of heartbeat packets being processed in the underlying TLS layer. The heartbeat can be initiated by either peer of the connection, exposing both ends of the connection to potential issues. According to the standard, only one heartbeat message can be in transit at a time from each endpoint, which may limit the speed at which they can be processed. Unfortunately, even between two well-behaved and honest endpoints, the heartbeat extension as originally implemented in OpenSSL was not safe to use because private data was always being leaked. The structure being sent and received between the endpoints in the TLS layer is defined in the RFC. Although it may appear harmless at first, the danger comes from a variety of sources to create a potentially severe vulnerability if implemented without care. The first parameter, type, indicates whether it is a heartbeat request or response. Second parameter, payload length, is where the trouble begins, because it opens the door for a peer to lie about the size of the contents contained in the remainder of the message. Third parameter, payload, is a blob of user-defined data whose length is supposed to be that of payload length. Finally, the fourth parameter, padding, whose length can be calculated by subtracting the sizes of the other variables, should be at least 16 bytes of random data. The purpose of padding is often to create a byte-aligned message size, but in this context it is to make it more difficult to discern it from regular traffic. This is because if a man-in-the-middle attacker is able to intercept and isolate heartbeat traffic by distinguishing them by their size and frequency, they will have a reduced search space for discerning the decryption keys. This is of course computationally complex for the attacker, but reducing the surface area of possible attack vectors is rarely a mistake. The OpenSSL implementation of the heartbeat extension references the heartbeat message structure in the RFC and processes the message inside of the functions TLS1 process heartbeat and DTLS1 process heartbeat. They read the contents of the incoming request, process it to create the corresponding response, and finally write it back to the connection. The main cause of the issue is that the payload size is read into the variable payload from the remote peer's data stream without checking if it appears reasonable. Afterwards, that size is used to copy data from memory and written back to the remote peer. A failure to validate user input is a common bug, but rarely is it as consequential as this, where a remote peer, without physical access to the machine, is able to read the private memory of a remote host. One thing to note is the padding variable is not filled with zeros or random bytes for TLS connections, but it is for DTLS connections, even though the specification requires it for both. This means that even with two well-behaved peers communicating with each other using heartbeats, private data was being leaked within the 16 bytes of padding. Not only is there no bounds check on the payload length, it did not adhere to the RFC requirement specifying that the entire message must not exceed 2 to the power of 14 bytes, or 16 kilobytes. The consequences of this lead to the attacker being able to request up to 64 kilobytes of memory instead of 16 kilobytes per heartbeat request. One interesting mitigation is that if the attacker is too greedy, it's possible the memory copying function will read into memory that does not belong to the process it is running within and likely result in a seg fault, crashing the victim application. The chances of this occurring can be reduced by requesting smaller amounts of data in the heartbeat. Another is that when requesting memory with malloc, the operating system will often give you the same memory pointer as was previously freed, meaning the attacker may end up reading back the same memory as before. One way an attacker could improve their attack is to create simultaneous connections to guarantee that different areas of memory were being read. Heartbleed is generally portrayed with misbehaving clients trying to trick servers into releasing privately held data, but the vulnerability is equally as dangerous in the opposite direction, where a devious server could potentially exploit clients connecting to it. This attack vector was dubbed reverse Heartbleed, despite it exploiting the exact same code. The official CVE for this vulnerability gives a stark description of what is at stake, noting that the most important data possible may be exposed. As Heartbleed was not a design flaw in the protocol, but a failure in the implementation, projects like GNU TLS and WolfSSL potentially provided an alternative which did not leak valuable data. Unfortunately, their use was limited because OpenSSL was, and still is, the majority of backends for secure communications. Several months after the pull request was accepted, on the 14th of March 2012, OpenSSL 1.0.1 was released. It was the first official release to contain Heartbleed. Maintainers of dependent projects quickly integrated the new version into their own software. The set of projects dependent upon OpenSSL is vast, as it is one of the most used user space libraries in all of computing. Close to every server, phone, switch, TV, and personal computer would likely import this bug from at least one piece of software it ran. OpenSSL is so ubiquitous that it would not be unexpected that individual devices could be vulnerable from multiple sources of software running on it. Although the vulnerability only exposes itself when the user creates a TLS connection, this use case is one of the central purposes to linking with the OpenSSL library. Major software infrastructure of the Internet, including Apache and Nginx, as well as common operating systems like Debian, Ubuntu, Android, CentOS, Fedora, FreeBSD, and many more were affected. On the 1st of April 2014, just over 2 years after the release of 1.0.1, Neil Meether from Google's security team, while doing a line-by-line analysis of OpenSSL's secure sockets layer, discovered Heartbleed. Less than a week later, Google's security team privately reported the vulnerability to the OpenSSL team. Codenomicon, a Finnish cybersecurity firm, independently found and reported the issue just 2 days after Google on the 3rd of April 2014. The two companies had very different approaches to managing the disclosure. Google chose to notify OpenSSL and prepare other vendors before publicly announcing. Codenomicon decided to create a website and a logo and advertise their success in finding the issue. Google chose not to notify the federal government, according to the White House at the time. OpenSSL released a security advisory in relation to the CVE and described how to eliminate the vulnerability by either recompiling without heartbeats enabled or upgrading to the newly fixed version. At the time of disclosure, 17%, or around 500,000 of the Internet's secure web servers certified by trusted authorities were believed to be vulnerable to the attack. Ars Technica reported that 2/3 of the web were exposed. Cloudflare revoked all its TLS certificates and estimated that publishing its certificate revocation list would cost the issuer, GlobalSign, $400,000 that year. Bruce Schneier, a computer security expert, said, "Catastrophic is the right word. On the scale of 1 to 10, this is an 11. Forbes said, "Some might argue that this is the worst vulnerability found since commercial traffic began to flow on the Internet." The Tor project advised, "You might want to stay away from the Internet entirely for the next few days." Although evaluating the total cost of Heartbleed is difficult, eWeek estimated $500 million as a good starting point. A spokesman from the UK Cabinet Office told the BBC, "People should take advice on changing passwords from any websites that they use." Because of the nature of the vulnerability, there are likely many victims we won't know about, because OpenSSL by default does not leave logs for heartbeats. The chaos following the disclosure will have also hidden many victims, with the tech news being overwhelmed at the time. However, there are some documented victims, one of which was Statistics Canada, a Canadian government agency who had its servers compromised and temporarily took its services offline. Another Canadian government agency, Canada Revenue Agency, temporarily shut online services over Heartbleed security concerns. They later reported a theft of social insurance numbers belonging to 900 taxpayers and said that they were accessed through Heartbleed during a 6-hour period on the 8th of April 2014. After the discovery of the attack, the agency extended the taxpayer filing deadline and said that it would provide credit protection services at no cost to anyone affected. On the 16th of April, the Royal Canadian Mounted Police announced they had charged a computer science student in relation to the theft with unauthorised use of a computer and mischief. The UK parenting site Mumsnet had several user accounts hijacked and its CEO was impersonated. The site later published an explanation of the incident, saying it was due to Heartbleed and the technical staff patched it promptly. In August 2014, it was made public that the Heartbleed vulnerability enabled hackers to steal security keys from Community Health Systems, the second biggest for-profit hospital chain in the United States. The breach occurred a week after Heartbleed was made public, and hackers stole 4.5 million patient records. During the period where Heartbleed was an exploitable zero-day, that is a security hole that is in publicly released software but unknown to anyone who may be able to prevent its use, there were reports the NSA were made aware of the vulnerability shortly after its introduction. Robin, the original author of the defect, denied any intention to submit a flawed implementation. The NSA, in somewhat typical fashion, denied the claim that they were responsible or knew about it. I leave it to the listener to appraise their honesty. A fixed version of OpenSSL 1.0.1g was released on the 7th of April 2014, on the same day Heartbleed was publicly disclosed. The fix itself was not complex. Most importantly, it was just the addition of a simple bounds check. A much more challenging component of securing internet traffic was distributing it as quickly as possible. The easiest solution for most users was to upgrade through their package management system as part of their operating system. However, software is often built outside the operating system ecosystem, and the developer would need to rebuild and distribute their software with a fixed OpenSSL version, which may not always be straightforward. In the wake of Heartbleed, there was a lot of criticism thrown in many directions. Despite OpenSSL creating the issue, most of it appeared to be directed at large corporations for not supporting projects which they relied upon so heavily. Steve Marquess, who at the time was the CEO of the OpenSSL Foundation, said, "I'm looking at you, Fortune 1000 companies, the ones who have never lifted a finger to contribute to the open source community that gave you this gift." A series of mitigations, both technical and strategic, were enacted to try and reduce the possibility of something similar happening again. The industry's collective response to the crisis was to create the Core Infrastructure Initiative, a multi-million-dollar project announced by the Linux Foundation on the 24th of April 2014 to provide funds to critical elements of the global information infrastructure. The initiative allows developers to work full-time on their projects and to pay for security audits, hardware and software infrastructure, travel and other expenses, with OpenSSL being the first to receive funding from it. The Core Infrastructure Initiative was created and funded through donations from major tech companies such as Amazon, Google, IBM, Microsoft, Facebook and Intel. It was superseded by the Open Source Security Foundation in 2020, extending its remit to providing code signing services and improvements to software supply chains. Google established Project Zero, which is an internal group tasked with finding zero-day vulnerabilities to help secure the web and society in general, who subsequently found Spectre and Meltdown vulnerabilities in the years following. OpenBSD created LibreSSL, a fork of OpenSSL, and also claimed it was broken beyond repair and suggested starting again. OpenSSL core developer Ben Laurie claimed that a security audit of OpenSSL would have caught Heartbleed. On the 25th of August 2016, more than 2 years after Heartbleed was discovered and fixed, in OpenSSL version 1.1.0, the Heartbleed extension was removed for TLS and disabled by default for DTLS. Following 2 years further on again in September 2018, OpenSSL version 1.1.1 removed it for DTLS connections as well, citing that it created unnecessary attack vectors. In the years following Heartbleed, many groups looked to see how many people might still be running vulnerable versions of software. One group, Shodan, said in January 2017 that nearly 180,000 internet-connected devices were still vulnerable, and that 18 months later that number had dropped to 144,000, and by July 2019 that number again had dropped to 91,000. While researching this event, I formed my own thoughts, which I think differ significantly from the narratives, and I wanted to share them. Features being enabled by default is rarely necessary, especially when there is no customer demand for it, and the only reason seems to be an academic whimsical research accolade. The core OpenSSL team claimed about not having enough resources. I'm not disputing the truth of this statement, but if there is limited resources available, why are they dispensing them on reviewing extensions like this, which should be at the very back of the queue? I think the possibility of sabotage is small, but still underestimated. The public zeitgeist may have forgotten about NSA programs like Bullrun, a highly classified NSA program to crack encryption of online communications and data. But there is an underappreciation of how pervasive threats like this not only still exist today, but are almost certainly greater in scope and scale than ever before. To be clear, I think the chances this was incompetence is still by far the most likely cause. And on that note, I think the level of incompetence was minimised far more than it should have been. The fact the padding on TLS connections was continuously leaking private data, even before it was further abused by manipulating the payload length, is an appalling level of ineptitude. The media failing to report that the padding was always leaking private data is disappointing, but expecting modern media to disseminate accurate information is a lot to ask. The fact that words like must and must not in the RFC were ignored out of convenience and carelessness is not acceptable in anything that might be related to the security of billions of devices. Even though the protocol, if implemented correctly, was safe, it was still full of potential tripwires that were completely unnecessary. The payload size should be calculated based on the underlying size of the message, not a hierarchy of sizes. Having a variable size heartbeat is just not necessary when the padding was already a variable size. The processes involved in getting code into the master branch were clearly insufficient given the range of possible threats. Large companies need to be ready to upgrade their software quickly in events like this. The fact it took some months or even years to do so is unacceptably dangerous to everyone. Finally, I think the belief open source software is more secure is a convenient thought for developers using those libraries more than it is true. That because a piece of software has more users, it somehow makes it more secure is false. Developers using open source software don't spend any additional time examining that code for vulnerabilities. The incentive for academics and others to create new features vastly outweighs the incentives for those same people to be reviewing and fixing potential security issues. Fundamentally, I think there is a large disconnect between what engineers and the public think open source means and what it actually is. One question I wanted to ask before finishing is just how much resources do you think governments are putting into sabotaging open source projects?